Hello and welcome. Today I'm going to cover the topic of integration. Specifically, I'm going to be covering the topics of use substitution, integration by parts, trigonometric integration, trigonometric substitution, integration by partial fraction decomposition, which I will refer to as PFD for the sake of the video, improper integrals, and arc length. Use substitution is fairly simple, and it is essentially just locating a problem area within an integral and replacing it with a u to make it easier to integrate. In this case, we're going to let u equal x minus 1 and take the derivative of x minus 1 so that du is equal to dx. After doing this, we get the integral of 1 over u squared du, and then we can use the reverse power rule for this to get negative 1 over u plus c. But then we still need to change the u back to the x minus 1, so we get negative 1 over x minus 1 plus c. Now let's look at a definite integral using use substitution. We're going to look at the integral from 0 to 2 of x over x squared minus 5 squared dx. This one actually works out fairly nice, because when you let u equal x squared minus 5, you get that du is equal to 2x dx, and we already have an x on the top, meaning that we end up getting 1/2 times 1 over u squared du. Something you have to remember when using u substitution on a definite integral is to change the bounds. So now we use the reverse power rule to get negative 1 over 2u evaluated at negative 1 and negative 5. So you can actually evaluate this as is, or you can change the u back to the x squared minus 5, and it actually works both ways. So you get the same thing as the answer being 2/5. Integration by parts relies upon this formula up here, where it's saying that this integral is in the form of the integral of u dv, and now we just have to assign these either the role of u or dv. In this case, we're going to let u equal ln x and dv equal x dx. Now typically you're going to want the simplest term to be the u, but in this case we don't know how to take the antiderivative of ln x, so we're going to let u equal ln x. And then we plug these values into this equation, and we end up getting this antiderivative. Now this is a case where you're going to want to let x equal u because it's easy, because we actually know how to take the antiderivative of cosine of x. So we're going to let u equal x and dv equal cosine x. We're going to take the antiderivative of cosine to get sine, and of course the derivative of x is just dx. It's just 1 dx. And so then we're going to use this equation to get this antiderivative. When it comes down to it, trigonometric integration just relies on a simple u sub, but the difference is that in a lot of cases with trig integration, you're going to have to change one of the terms to a trig identity to make it easier to integrate. In this case, we had to change the sine squared x into 1 minus cosine squared x times sine x dx to make it easier to integrate. And then we distribute the cosine squared x, and then we do a u sub to let u equal cosine x and du equal negative sine x, and we get, which allows us to get rid of this sine x right here, and then we get u to the 4th minus u squared du, which is u to the 5th over 5 minus u cubed over 3 plus c, and then we change the u back to the cosine x to get cosine to the 5th x over 5 minus cosine cubed x over 3 plus c. The most important thing with trigonometric integration is just remembering your trig identities. Trigonometric substitution is maybe the most complicated out of the methods of integration I'm going to go over today, unless you have to do integration by parts 2 to 3 times. But what it does is it changes the x's to trig identities in order to make this easier to integrate. So in this case, we're going to be looking at the integral of x over the root 9 minus x squared dx. So we're going to first start off by a substitution, and we're going to let x equal 3 cosine theta and dx equal negative 3 sine theta d theta. And what we do first is we're allowed to factor out a 9 from this right here because we let x equal 3 cosine theta, so we ended up with 9 minus 9 cosine squared theta. So we factor out a 9 and we took out a 3. So now we have negative 9 sine theta cosine theta over 3 root 1 minus cosine squared theta d theta. And then negative 9 over 3 is negative 3, and root 1 minus cosine squared theta is the same as sine of theta, and so we're able to move that down, and we're able to cancel out the signs to get negative 3 times the integral of cosine theta d theta, which is just negative 3 sine of theta plus c. But then we still have to change negative 3 sine theta back into x terms. So in order to do that, we use this knowledge. We know that cosine of theta, and we derive this from here, is equal to x over 3. And so we're able to set up a triangle with the adjacent side being x and the hypotenuse being 3. And using the Pythagorean theorem, we can derive that the other side is root 9 minus x squared. And we can use this triangle to find what negative 3 sine of theta plus c is, and it's just going to end up being negative 3 times the square root of 9 minus x squared over 3 plus c, and then we can cancel the 3's to get negative root 9 minus x squared plus c. Now we're moving on to, I think it's our last technique of integration, which is using partial fraction decomposition, or P of d. So with this integral, the first step is probably going to be to factor this out, and then we're going to separate this area right here, and we're going to move it over here so we can deal with it separately. So we're going to use partial fraction decomposition so that 1 over x minus 6, x minus 4 is equal to a number a over x minus 6 plus a number b over x minus 4. And so we're able to multiply both sides by x minus 6, x minus 4 to get 1 equals a x minus 4 plus b x minus 6. And then we're trying to get the values where these numbers are going to equal 0. So at x equals 4, 1 is equal to negative 2b, so we get that b is equal to negative 1/2. And at x equals 6, 1 equals 2a, so a is equal to 1/2. And so by this, we're able to factor out a 1/2 and get that it equals the integral of 1 over x minus 6 minus 1 over x minus 4 dx. And then we're just able to use a simple u sub to get 1/2 times the natural log of x minus 6 minus the natural log of x minus 4. I'm sorry, the absolute value of x minus 6 and x minus 4 plus c. And then you're able to use log rules to get the natural log of x minus 6 over x minus 4 plus c. There are two types of improper integrals. There's the first type where there's an issue with the boundaries or a number on the boundaries that makes the denominator equal 0. So here, the boundary of 4 is going to make it 1 over 0, which does not exist. And the second type is just where the integral goes to infinity. And so for both of them, you're going to want to reset it up as the limit as a variable approaches the problem number either from the positive or negative side, depending on the way that you're approaching the integral, times, of the integral, And you're going to set up and evaluate the integral as you would normally, except this should be right here. This should be 4 from the negative side, and that's actually going to be negative infinity, which is divergent. And then you're going to, for this one, you're going to set it up the same way, and we're going to actually do a u sub for this one. So you get 1/2 the limit as a approaches infinity, and I didn't include the boundaries because we did a u sub of the integral of 1 over u squared du is equal to 1/2 the limit of a as a approaches infinity of negative 1 over x squared plus 4, evaluate at a and 0. So that's going to end up equaling 1/8. And because there is an existent answer, it is convergent. For arc length, you really just need to remember the formula and how to use it, really. So there's usually a given interval, and those correspond with the numbers on the integral. And dy dx is just going to be the derivative of the given function. So in this case, the derivative of 2x plus 1 squared is 4x plus 1. And then you just plug that into the equation, and I used a calculator to get the answer being about 16.136. Alright, now it's time for some practice problems. You can pause here and attempt them, and after that, I'm just going to go over these. Alright, so first, for this one, the first thing you do when looking at an integral, you have to check if it's improper or not. And for this one, it does seem like it is. So we're going to have to rewrite it as the limit as t approaches 3 from t to 7 for 1 over x minus 3 squared dx. And then we use a u substitution, and then we just evaluate it like that from t to 7 du, and then we evaluate this, and it goes to infinity because it's a 1 over 0 case and it is divergent. For this one, this is just an integration by parts problem. So we said u equal to x because it's the simplest term, and we know how to take the antiderivative of tan squared x. So we're going to set tan squared x equal to dv, and then we plug it into the equation. So we have x tan x minus the integral of tan x minus x dx, and we get the solution, it being x tan x minus x squared minus ln the absolute value of secant x plus x squared over 2 plus c. And then for this one, we just need to plug it into the equation for the arc length after finding the derivative. So the derivative of ln cosine x is just negative tangent x, and 1 plus f prime of x squared is going to be secant x because of trig identities. And so then we set up our integral from 0 to pi over 3 for secant squared x dx. And then we get the antiderivative being ln secant x plus tan x evaluated at 0 and pi over 3, which is ln 2 plus root 3. Thank you for watching.